In this video, we're going to look at example 3 in section 8.6. So this is another example where we're going to determine the interval of convergence of a given power series. So we're going to follow the same steps that we did in the previous example. We're going to first use the ratio test to determine the interval of convergence, and then test the endpoints of the interval to see if we converge or diverge on those endpoints. So I encourage you to pause the video and work out this ratio test on your own first, and then skim ahead in the video and compare your work. It's important to watch the video really slow though, slow it down when you are checking your work so that you see all of the cancellations and all of the steps and some extra tips along the way. All right, well, if you had a chance to look at that ratio test on your own, let's go ahead and compare. So we're going to set up that ratio test, the limit as n goes to infinity of a sub n plus 1 over a sub n. So here, our a sub n looks like x minus 2 to the n over 2 to the n square root of n. So it gets a little bit more complicated, but that's okay. We'll just handle it one term at a time. So if we're looking at the n plus 1 term, we have x minus 2 to the n plus 1 over 2 to the n plus 1 square root of n plus 1. So I'm going to multiply the reciprocal by the reciprocal of an. So that would look like 2n square root of n in the numerator divided by x minus 2 to the n in the denominator. So now let's go ahead and take a look at what can cancel for us. So I have this x minus 2 in the numerator and denominator, so I can cancel n of them from each. I have a 2 and a 2 in the numerator and denominator. I can cancel n out from each. So let's go ahead and make that cancellation and see what else we still have. So we have x minus 2 in the numerator times square root of n divided by 2 in the denominator times square root of n plus 1. So now we can look at our terms inside the limit and consider which of these terms are affected by the limit. So we see that only those, including the n, are affected by the limit. So what I can do is bring out that square root of n over square root of n plus 1 and just keep that term with the limit and bring out this absolute value of x minus 2 over 2 because it's not playing with the limit as n goes to infinity at all. So this is equal to absolute value of x minus 2 over 2. Notice 2 is already positive, so it's only going to be x minus 2 that might be negative, so I need to keep the absolute values there. So now I can multiply that by the limit as n goes to infinity of square root of n over square root of n plus 1. I don't need the absolute values there anymore because I know n is always positive. All right, so let's go ahead and just simplify a few more things. So because my numerator and denominator both have square root, I can include that entire fraction with one square root. So this becomes the absolute value of x minus 2 over 2 times the limit as n goes to infinity of the square root of n over n plus 1. So it turns out in this situation, we can bring that limit inside that square root. So this becomes the absolute value of x minus 2 over 2 times the square root of the limit as n goes to infinity of n over n plus 1. Now we should recognize this limit. We just saw it in the previous example. We used the L'Hopital's rule to compute that this limit is equal to 1. So this just becomes, using that L'Hopital's rule, the absolute value of x minus 2 over 2. So now we don't have a limit at all. We've finished computing that limit. So this is that final answer that we get after computing the limit. So this value is our R value. So I'm going to say value of R from ratio test. So what needs to be true about that value of R? Well, we need r to be less than 1. So that means for convergence, using this ratio test, we need x minus 2 over 2 to be less than 1. So let's see how we can solve for x here. If I multiply both sides by 2, that 2 cancels in the denominator, so I'm left with x minus 2 has to be less than 2. So notice this gives me that x minus 2 has to be within 2 and negative 2 in order for that absolute value to be less than 2. And so now I can just solve for x by adding 2 everywhere here. So this gives me the interval that 0 has to be less than x less than 4. So the series converges on this interval when x is between 0 and 4. Okay, so we know we have convergence there, but now we still have the question, what about the endpoints? So now, what about endpoints? So the endpoints of our interval are when x equals 0 and when x equals 4. So what happens there? All right, well, no big deal here. We just need to evaluate our series at x equals 0 and 4 and determine the convergence of each series. All right, so let's go ahead and do that. So let's consider when x equals 0. So what does our series become? I'm going to go ahead and copy it down again just so I can see what that series is. If you still have your paper out in front of you and you can just flip through it, go ahead and do that. All right, so here we are. So when x equals 0, we get the series of n equals 1 to infinity, 0 minus 2 to the n over 2 to the n root n. All right, so we can just rewrite this and continue writing it or simplifying it until we can get a series of a form that we can recognize. So notice that numerator, we have negative 2 to the n. Well, I can just split that up as negative 1 to the n times 2 to the n. So what this is saying, negative 2 to the n, is I have negative 1 times 2, all of those to the n. So I have n negative 1s, n 2s, so I can split up like that. So I can rewrite this as negative 1 to the n, 2 to the n. And the reason why I want to do that is because I'm recognizing with this term, negative 2 to the n, an alternating series. So I just want to write my series in that alternating series form, if I can. Let's continue working here. Oh, nice. I see these two n's cancel. So I'm left with the sum of n equals 1 to infinity of negative 1 to the n over root n. And so now I can recognize this as an alternating series. So let's go ahead and check for convergence. So let's check our three conditions. And before doing that, I can identify that my bn is going to be 1 over root n. So I need the bn's to be positive. I need their limit to go to 0, and I need them to be decreasing. And we can go ahead and check. We can see actually right away that all of these are satisfied. Yep, 1 over root n is always bigger than 0. The limit as n goes to infinity of 1 over root n is just 1 over infinity, which goes to 0. And we see that root 1 over root n plus 1 is going to be less than 1 over root n. The n that we're using are integers. So when we square root a whole number here, we're going to get a larger number if we have a larger number in the square root to start with. So the square root of a large number is going to be bigger than the square root of a smaller number, meaning the denominator of this fraction is larger than this one, meaning this fraction is smaller. Feel free to take out some more steps there if you want to really see that. But I trust you can work out the algebra there on your own. Okay, well, this is cool because this shows us that the series converges. And I'll even just say specifically at x equals 0. So now we have a conclusion about that first endpoint. All right, let's consider what happens then at the other endpoint. So we need to check when x equals 4. Their other endpoint was when x equals 4. So we need to go ahead and check that. So when x equals 4, let's consider what that series is going to look like. So I have it up here on my page. So we can just plug in 4. So the sum n equals 1 to infinity of 4 minus 2 to the n over 2 to the n square root of n. So let's go ahead and just work that out, simplify a little bit. So we get n equals 1 to infinity. Now the numerator 4 minus 2 is just 2. So we get 2 to the n over 2 to the n root n. All right, what happens there? Well, that's cool. The two n's again cancel. And we're just left with the sum of n equals 1 to infinity of 1 over root n. So does this series look familiar? Well, here we have a p series with p equal to 1/2. The power on the n in the denominator is 1/2. So what do we know about p series with p equals 1/2? Well, it diverges. So therefore, at x equals 4, the series diverges by the p series. And we could say p series test if we want. Okay, so now we get divergent at x equals 4. All right, so now we, though, have determined what happens on the endpoints of our interval. So at 0, we get convergence. At 4, we get divergence. So let's just go ahead and summarize that statement here. So final conclusion, we can say our interval of convergence for our series is the following. We're going to include 0. We're going to go up to 4, but not include it. We want to write it in using inequalities. We'd say that, well, x needs to be between 0 and 4, but it can be equal to 0, but has to be strictly less than 4. Awesome. So there we go. We found our interval of convergence.